So welcome back to System Software. I'm recording now. Let's get back into the class. So we're here in the middle of the system programming section, where we learn how to use our kernel, how to use the functions that it gives us, the system calls that it gives us, in order to manipulate these kernel abstractions that abstract away the hardware. So we can use the processor, we can use storage, we can use memory, all without having to know the details of the hardware, and with these more convenient abstractions. So last time we went over using the file system. We covered system calls. So what's the most important thing to remember about system calls whenever you make a system call? Check for errors. Make sure you do error checking. Error checking is up to you, the developer. So make sure after every system call you're checking its error handling. And how can you find documentation on the error return? Like, how do you figure out what to check for when there's an error? Yeah. Can you look in the manual? Yeah, read the manual. RTFM, right? You can use the man command to read the manual. So, and what was this number? Does anyone remember what this number was to the manual? Section number. So section 2 are the system calls. Section 3 are the library calls. Open is one of the system calls that the kernel exposes to you. So the open for opening files. The return value and error section are the key parts to look at. Yeah.
Sorry, this is just a quick side question. You mentioned the abstraction. What is that again? Did you put the reference?
Oh, so if you remember when we talked about the file system, the notion of a file is an abstraction because it doesn't literally translate to bytes on disk. It's an object that's maintained by the kernel that allows you to read and write bytes to it. And so you can certainly use a storage as the backing of that abstraction, but you could also use network I/O or pipes, as we'll see. But the file abstraction is just like if you learned about abstract data types. Did you learn about abstract data types? Nobody learned about ADTs? CS1?
Yeah. Oh, yeah.
You learned CS1, ADTs, abstract data types, right? So you can implement a list in multiple ways. You can use an array, you can use a linked list, a doubly linked list, lots of ways to implement a list. The list data structure is an abstract data structure. It doesn't include the details of how it's implemented. And so these file and process abstractions are much the same thing, where the details of how they're implemented on disk or over an Ethernet card, you don't need to know that in order to actually use the abstraction. And the kernel exposes this abstraction to you through its system calls. Okay, so we learned about errors. We did the error number example. Questions on so I went over the file example first, where you're opening and reading a file. Questions on this example from last time. So we used the open command here, given a path to get ourselves a pointer, so to speak, a file descriptor that refers to that open file, read to read bytes from it, and close to tell the kernel we're not using the file anymore. Yeah. Right. Yeah. So FO. So yeah, we talked about this a little last time. Who can tell me the difference between fopen? Yeah.
Fopen just opens like a file. Like fopen opens like a file, and then open just opens like.
Well, so both open a file. So fopen is in section 3 of the man page, and it's the C library version of opening a file, and it gives you additional functionality. It gives you buffering, it gives you other features like using fprintf, for instance. So you can use fprintf, which is not a system call. The kernel doesn't provide fprintf. But with fprintf, I can print a string, I can put formatting in that string, it'll do buffering for me.
Regular open doesn't do that?
Regular open doesn't do that. So with the open, so for instance, fscanf, or fgetchar. These give you characters, they give you formatting, they give you buffering, and under the hood they're calling read. And all read gives you is a way to read raw bytes from the underlying file. So fopen is calling open, and then open is calling the kernel to do its job. So you can think of this as a different file abstraction as strings. that have other features to them, whereas the kernel file abstraction is just bytes, reading and writing bytes. I don't know, does that answer your question? Whoever asked it? Wasn't he over here? Oh, okay. All right, other questions on the file example? All right, let me review the MyLS project, the next project in the class. And so in this, we're gonna create our own version of LS. What does LS do? Yeah, list files in a directory. And so to make it a little less, so you're not gonna copy the LS command exactly, but I've given you a special output that you should have for LS and a specific format so that you'll be able to use various aspects of the file system abstraction. So at its core, it's going to list the contents of a different given directory. The usage is here. So by convention, when you see these brackets around an argument, so this is the program name that you're running. This is the argument. So how do you read arguments in a C file? Actually, no. That's how you read from standard in or from a file. Yeah. Yeah, argv and argc. Did you guys learn this in CS1 or intro? They didn't teach about argv? Some people did a little bit. Okay. So I have example code that'll show you this. So for instance, here, this is example code of using argv. But that's how you read the command line arguments. They get passed by the C runtime as an argument to your main. Yeah.
Just to confirm, argc is how many arguments there are, and argv is the array of them.
Exactly. Yeah. Exactly right. So argc is the number of arguments. Argv is an array of strings. That's why it's a double pointer. So the char star is a string in C, and so a pointer to a string in C would be char star star.
Do we put vim stat.c yet now?
So this is not stat.c. This is a different one. This is files. And so the first argument, argv0, is the name of the name of the program that you ran. It's whatever the user passed as the first thing on the command line will be arg0, and then after that will be each of these space separated or white space separated. And so if you want to check, so in this case I'm checking whether there are fewer than 2 arguments, because if there's one argument it means, or if there's one argv, the first one is myls. So I'm checking whether there are at least 2. So if there are more than 2, I don't read that. And then here I'm taking the second argument. Remember, C is base 0. So I'm taking the second argument, which is given here. So in your program, you'll have to check whether there is an argument first. If there isn't an argument, so these brackets here mean optional arguments. So for instance, if you look at ls, this is just a convention in Unix documentation that if there's brackets, it means that argument is optional. So file, you don't have to provide a file to ls. What does it do if you type ls without giving an argument? Working directory, exactly right. So it's the same thing here, the working directory. An easy way to get the working directory is use the dot directory. It's one of the benefits of having a dot directory is you can always refer to the working directory or the current directory without having to know its path. You can just use the dot directory to do it. Okay, so myls takes a directory or defaults to the working directory, and it outputs a list of every file in the directory. Yeah.
You said we have to include that the argc and the argv in order to take in the console.
Yeah. Well, you just, so it's passed to main. Yeah, it's passed to main. So if you've ever wondered why argc and argv are here, why you have to do that, that's what it's for. It's the command line arguments being passed in. So the C runtime is kind of designed around this command line interface. Okay, so the output is a list of all files in the directory. So the first column is the names. So I've given a list of various columns of information that you'll provide for each file, and all of this can be gathered from the system calls that I'm going to show you today. So the name of the file, the number of hard links to the file, so that's the number of other references to that file in other directories, the type of file, the size of the file. If it's a directory, then give the number of entries. If it's a file, then give the size in bytes. And if it's a regular file, that is just not a directory, not a device, then preview the first 16 characters and spit them out. So this is designed to kind of get you comfortable with using the various system calls and using the documentation to figure out how to get each piece of the struct that's given to you, of the data that's given to you back. To make things a little easier, I've given you the like exact format strings to use for fprintf. You could just use printf for this, and these are the exact format strings to use for each of these. So that when we do grading, your output will be exactly what's expected.
You said this is going to standard output, not the file output?
Yeah, standard output. Yeah. Well, standard out is a file, but yeah, you can use printf. So this is what it looks like when you have the correct output. We have the name of each file in the directory here, the number of hard links pointing to that file, what type of file it is, so it's either a directory or a regular in this case, size of the directory, that is number of elements in the directory, size in bytes of regular files, and then there's a little, for regular files, there's a little preview of the contents of these files. Yeah.
In the output format table you gave us,
Yeah.
for type, it just says string literals.
Yeah, so here, I have a little note here describing this. These are described in the output contents. And I have some example code today of how to do that, these are the string versions of the file type. But yeah, good question. And there was another question?
I'm just asking, like, what are we typing for now?
For these string literals?
Yeah.
They're here. They're in the output contents. So there's a little note under this table saying, well, here's where you get PRI, DMAX. Here's where you get the string literals.
That has it.
Yeah, it'll hopefully that's sufficient. All right, so that's the I/O of the MyLS tool. Questions on that? I'm sure you have a question on how to do it, but questions on the specification of the problem. Yeah.
So how we print that method, we create vim stat.c right now.
Well, that's just editing a file. Stat.c will open a file. But this, you can name the C file whatever you like, but the program should be called MyLS.
I know. I already created it. I know, but like, is stat.c file relevant to the MyLS?
Yes, stats.c is where you'll get most of this information. So let me get into stat then. If there's any other questions on the MyLS project description. Okay, so there's actually a program called stat, which displays file metadata that's stored by the kernel for each file. So let's look at, say, airno.c. So it gives you the name of the file, gives you the size in bytes, I think, number of blocks that it uses on disk, and it gives you other metadata like how many hard links you have, permissions, dates of when it was accessed, modified, etc. And all that. So this is just a program that asks the kernel for file status and then prints out that information. To do this programmatically in our C program, there's a system call. So I just did man2stat, so that's system calls. There's a system call called stat, which if you give it a path and a pointer to a stat buffer structure, it will populate that structure with a set of data. And so it populates that, where is struct stat. There's the structure. Oh, whoops, so I have a little mistake in here. So man3 stat will give you the data structure, documentation of that stat buff data structure. And so this is the names of all the fields in that stat data structure that's given to you by the stat system call. So here's the file type and mode. Here's the file type. Here's the number of hard links. Here's the size in bytes. And so this is where you're going to get most of the information for this output. What about the file name? So there's nothing here about the file name. Where's the file name come from? Where's the file name stored? Remember the Unix style file system design. Where's the name of the file stored? If it's not stored with the file metadata that the kernel returns for you, yeah. Yeah, exactly. It's the directory. The directory has the name, and it points to an INO number. It points to this unique identifier for the file. So the name itself is not stored with the file itself. And part of the reason for that is you could have multiple file names, multiple paths pointing to the same file. Okay, so let me go over an example of the stat data structure. Okay, so this program, just like before, just like all the examples here, it reads in one argument, and we don't even have to open the file. We can just call the stat system call.
Make it a little bigger.
Oh, yeah, sure. So here is a call to the stat system call. We need to pass it a pointer to a struct to store the resulting data. The kernel is not going to create that data for you. Instead, you pass it a pointer to the struct. The CS1 intro to C, they showed you structs, right? They showed you structs?
Yeah.
Okay, so you saw structs. And pointers, right? Learned about pointers. So here, I'm just initializing a new struct, the stat buff struct. And what does this ampersand do? Yeah, pass by reference gives the address of it. So this is going to be a pointer to this stat buff struct. So the stat system call, you just give it the path to a file, and you give it a pointer to some stat data structure, to some struct that you've already instantiated. And it's going to populate this data structure. This struct is going to be populated with all the information about that file that you asked for. Questions on that? Yeah.
So basically it's checking like if it's populated, if it's not, it would return -1.
Yeah, well, if the file doesn't exist,
Okay.
then yeah, it's going to return -1. So this is the stat system call, which if you look at the return value here, it returns -1 if it fails. Yeah. So this is it. If you do man3 stat, this is the structure definition.
So we're visualizing that and we're checking that file exists.
Well, the kernel will check whether that file exists. So if the file exists, so if you look at the documentation of the stat system call, if it successfully gets the file's metadata, then it returns 0. Otherwise, it returns -1. So if the file doesn't exist or it doesn't successfully run, you can just quit. You don't have to give information about that file.
We're using the stat struct from the stat.h.
That's right. Yeah, that's where it's defined. That's where the structure is defined. And yeah, you could look in that header file for the structure probably as well, but you could, the manual page is probably the easiest place to look to get all of the fields for this.
Page is that?
Man 3 stat.
Oh, page two.
Well, man 2 is the system call. Man 3 is the structure. Say again? Yeah, I'm actually not sure why. I guess because it's part of the I guess it's part of the standard library, the C standard library.
Because there's no manual entry for stat in section 3.
Oh, really? Oh, maybe that's Eustace.
Yeah, a bunch.
Oh, okay. I think that might be why I changed it. Okay, so it's actually in Man 2 in the stat. Okay, so my local machine's documentation is slightly different.
You can fix it for documentation cause machines.
Yes.
Apparently we can. That's kind of surprising, actually. So sorry about that. Yeah, it's here under Man 2 stat on, I don't know. This is 2020. Mine's 2023. So maybe it's older documentation. They must have moved it around. Because my local machine is 2023 here.
So yours is more updated than what
Apparently, yeah. But yeah, if you look on Eustace, that data structure, so that's why I had changed it actually. Yeah, so that data structure is here. Yeah.
How do you like scroll down?
Oh, so this is Vim commands. So you can do J or K to scroll up or down, or space to do it, or Control V, Alt V, or arrow keys should work too. All right, so that's the stat data structure, and here's examples of getting the information from the struct. Coincidentally, the same information you're going to need for this MyLS project. So here I'm just printing out the number of hard links that this file has. So this is st_nlink. Same for size. So I just get the, well, I'm going to use man3 here, but so I just refer to the struct field in order to get that data. So there's size and there's nlink. Questions on that? Yeah.
So like this is essentially how we're filling out all the fields for the assignment.
Yeah, exactly,
Pulling
exactly.
data from stat.
Yeah, for most of them. So one is the name. Most of them are hard links. Once you get to the last two fields, it's a little trickier because for directories, I've asked you to give the number of files in the directory rather than the size of the file, the directory file. And for regular files, I've asked you to give a preview of the file. So that means you're going to have to open and read the contents of the file.
Can you show an example of how to use stat again?
Sure. Yeah.
You just do like stat in the file.
You give stat and then a path, a string that holds the path, and then a pointer to a stat struct. So this is how you call. And so I've set the string here and created a data structure here. And so I just call stat. Other questions on this? So I'd recommend actually like hand typing out these examples. It's going to be tough to both write MyLS from scratch and also tough if you just try to do cut and paste. That's called cargo cult programming. It's going to be hard to do either way. So I'd recommend walking through these examples and maybe hand typing them so you kind of get the feel of how to use these system calls. And then sitting down and trying to pull these several system calls together to make the MyLS project. Just as a hint, I gave you the code that basically gets you started on MyLS. It opens a directory and lists all the files in that directory. So if you remember from last time, you call opendir, which gives you a pointer to a directory entry, and then you just loop over, you just repeatedly call readdir with that directory entry pointer. in order to iterate over each element of the directory, each entry in the directory. And then the only field you're going to need, I think one of the fields you need from that data structure is called dname. So I showed this last time, but this was all documented in I think in OpenDeer. This is described in the project. Yeah, so this is described in these man pages, these system calls. Okay, so that's the MyLS project. Other questions on the project, the system calls? Yeah.
So then print like the main
Oh, sorry.
directory, do like what you just showed us?
Yeah. Yeah, this is it. So this is how you'll loop over all the all the files in a directory.
And it'll put it in like the order we want, like in the column?
So I didn't specify any order. It'll be the order of that the kernel has stored the file entries. So that they'll be in ordering there. Ordering shouldn't matter. I mean, if you get a bad grade because of that, then let me know. But I'm going to tell the grader that order shouldn't matter. Yeah.
So for this assignment, do you want us to like use the methods in like the files, or just use the code, like as part of our sort of thing?
What do you mean? Use them?
So you said like we're making our own ls function,
Yeah.
and then like to meet the specifications of the assignment, do you want us to like literally call stat, or just use the same code that is used in stat.c?
Oh no, well, it's the same thing. I mean, the code in stat.c shows an example of using the stat call. So I've basically given you like examples that are going to be very relevant to that you can draw from to write the MyLS program. Yeah.
Sorry, the code that's in the website, we're not copying that and pasting it.
I mean, it's not the complete project. So if you just copy and paste it, it won't work. You'll have to put things together, arrange things together so that the MyLS project works. So these are just examples of using each of these system calls. So I've given you like an example somewhere of using these system calls. But when you go to write your program, you'll have to write the algorithm that creates this output. And to do that, you'll need all of these system calls. And so I haven't given you, the exact result, but I've given you examples of using the system calls so that you can use them in your algorithm at the right place, if that makes sense. Yeah.
So if we want to try to see what we did some over, then we should just untar the example that you gave us?
Exactly, yeah. So I've given you, and I'll post other public test cases. My grading staff has created some more test cases, but I've given you one example. And you can download and run your MyLS on this example to see if you get the output. So I've already given you, so this is the good way to do development, where you have some ground truth, you have some output that you want. And then as you do development, you can test to make sure that your program works the way it's supposed to. So these set of commands, I think you've used wget already in this class, right?
To make a new directory, right?
Yeah, well, for this?
Yeah.
Well, it'll expand into a new directory. So I can show you what this looks like. You just call w downloads it, and then you untar it. So that's expanding it. And so then we get this MyLS example folder. And it contains some subdirectory. You can use ls to look at it, which I actually just did. And then run your tool on that folder, that example folder, and this is what the output should look like when you run your tool. Modulo ordering differences, but otherwise, yeah.
There's some the order, like in the first column, you said it's fine, like dots, like dot in the first column.
Right. I mean, these should be in the first column, so this is going to be the directory entry order that the kernel represents the directory. And if you unpacked it, it's very likely that this ordering should match the order that they were added to the file system. So at least for our examples, if you untar them, the order should match. I don't see why they wouldn't. If you've modified them by hand, they may, or moved them around, they may not. But the order should match. But I'm not going to grade you if they're ordering differences.
Print statements you gave us, like, format, I don't think.
Yeah.
Like
Yeah, I'm using tabs here to make these tabs separated. That's why they're all nicely lined up. And so, for instance, this is limiting the name of the file to 16 characters. So if you just use these format strings to print out the data in each of the columns, you'll get this output. All right, other questions on MyLS? So try it out. You have all the system calls available. Try it out. Start small. Start with just listing the entries in the directory, which I've already given you an example of doing that. And then try, for instance, stat and say, all right, can I get this metadata? It doesn't have to be formatted yet. Just see if you can use the command correctly. And then, the next step is, okay, can you get the size of a directory, number of entries in a directory? And then finally, can you get the open and read the file to get the preview? And then once you have that, you can just double check against our test cases to make sure, your format strings are right, make sure you have no bugs. Make sense? Yeah.
Is it sensitive with the spacing, or does it really matter?
So spacing will be sensitive, but these, the grading scripts, I'll ask them to do exact spacing. But if you use these format strings, the spacing will be right, because this has the tab character inside of it. So that's why it's lined up like this. The tab character is ensuring that spacing works the way you expect. Yeah.
Sorry, one more question. With
Yeah.
the percent S on column 5, how does that guarantee 16 bytes?
Aha, that's a good question. So you'll have to make sure that you print out only the first 16 bytes of the file. So just as a little hint as to how that you can achieve that, remember that the read command, or the read system call, requires you to give the number of bytes you'd like to read. All right, other questions on MyLS? So you got a couple weeks for this one, or like a week and a half. But yeah, let me know if you have issues, confusion. Ask on EdSTEM, come to office hours. I hope it's not too bad. I think once you do it, it's not going to be that bad. The trickiest part is just the conventions of the system call, syscalls, but use the man pages to keep track of the fields and what the return value should be. Otherwise, the algorithm, from an algorithmic point of view, it's not that bad. Just have a loop, and you have several printf statements for each of these fields. And one little wrinkle is getting the number of elements of the directory. You'll have to open that directory and read it again. But otherwise, from an algorithmic point of view, it's pretty straightforward. It's just putting together all of the system calls, which makes this more complicated. All right, so let's move on to processes. So this and the next two lectures will prepare us for the next homework assignment, which is writing a little command line shell interpreter. So I'll go over that next week. But in order to do that, we have to learn how to manage processes. So we learned about managing the file system using system calls. And so today we're going to learn about how we manage processes. So recall that process. So what are processes in the Unix world? Let's say someone had it, yeah. So they're programs. Okay, very good. They're running programs. So I can have a program on disk like this files program, and it's just a bunch of binary data. But a process is a running program that's currently running. And why can't we just run the program? We could just tell the CPU, jump to this line of code in memory and just run it. Why bother having the kernel manage some fancy process abstraction? Why don't we just tell the kernel to start running this? Yeah.
Because it gets complicated as other processes are jockeying for time to get.
Exactly. So if we have a machine that's only going to ever run one program, we could make a special purpose machine that does that, maybe like a refrigerator or something. But if we want to have time sharing, if we have fewer resources or limited resources, then what the kernel can do for us is it can share these resources. And one of those resources is the CPU. And usually, I mean, even today, few machines have more than one or a few processors, at least for commodity commercial stuff. But you may have lots and lots of programs that you want to run at the same time. And rather than having to design a system where you sort of do custom transfers between these different running programs, the kernel provides you this general purpose abstraction called a process, and you can just tell the kernel, here's all the processes I want to run at any time you'd like. You can end and start these processes whenever you want, and it will handle actually starting and stopping these on the processor for you in the best way that it thinks is possible. Though there's all sorts of research on scheduling algorithms to decide when to switch between processes, when to prioritize certain processes. But you can just kind of trust your kernel in most of your probably common workloads to give you the impression that all these programs are running at the same time. So if you're on like a laptop right now and you have a browser open and your mail and whatever video game you're playing or YouTube videos, there's dozens of processes involved in all of those, and you have the feeling that they're all running at the same time, when in reality, they're sharing a single or a few cores on your machine, and the kernel is just switching very, very rapidly between running all these programs. Okay, so that's the process abstraction. That's why it's useful. So let's see how we actually use the process abstraction. Making a new process, making a new running program is pretty straightforward. To make a new process, you just call fork, and that will duplicate an existing process. And then when you want to have that process run a new program, you call exec. And that's it. It's really just two system calls in order to get a new running program on a Unix system. So if you read the reading from last time for the homework, this is a diagram of what this process looks like. So this assumes that you've got an already running process. So why is it that so if processes are only created from other processes, how can we be sure that we'll have a process to fork on a Unix system? Yeah.
During the bootstrapping phase, if one process is spun up,
Yeah, that's exactly right. During booting, exactly what you said. The init process is created and run when you boot the machine. So you in user space don't have any control over that, but as soon as you boot the system and log in, there's already processes running. And through other aspects of the system, logging in creates the bash process for you, creates this running bash process. When you run bash and you execute a program, bash is the parent process that you're forking from. And so bash will call fork for ls or whatever program you're running. And so given the process that's already running, you call fork, and now there are two processes already. And these two processes are virtually duplicates of each other. They have the same running program, same files, same memory, at least when it starts. And so you have two versions of the same running program. Doesn't seem very useful, right? Like now there's two versions of the same program. So okay, let me get to it. All right, so this is how fork works. It duplicates the program. And just to review the homework from last time, the homework question was, let me get the exact homework question. So when you have a fork and you make a new process, what happens to the open files in that process? If you remember from your reading. Yeah. They're duplicated, yeah. So this diagram shows it, where if we have two open files, so descriptors are a number assigned to each of your open files in a process. When we do a fork, the child inherits or duplicates all the open files. So you actually have two processes with the same file open at the same time. So if both write to that file, they're both going to be able to add contents to that file. Now, as the book points out, that may be undesirable because the data that you're printing out may be mixed up between the two. Yeah, kind of, well, yeah, kind of like yeah. So you can do locking or other communication to avoid that. And then here's a case of closing some of the file descriptors so that the parent and the child are now pointing to different files. But so everything is duplicated when you call fork, basically. Okay, so the question though is, if fork duplicates process, how do we avoid both processes just doing the exact same thing? So what did they say? What would they in the book? Yeah.
Would you like pause the parent one from the child and son?
So if they're the same running program, how will you know to pause the parent versus the child? So if you just call fork and then sleep or wait or something. You remember in the book?
Yeah.
I mean, remember in the book what they said to, so when you do fork, you have literally the same running program. So you write one C program, you call fork, and now there's 2 copies of that program running. And so they're going to have the exact same sequence of instructions if you don't do anything else. Yeah?
Get the process ID of the child and the parent.
Exactly, that's right. So the trick is that where you can detect a difference between the 2 processes is that the return value of fork, cleverly, returns something different depending on whether it's the parent or the child. So if this didn't happen, there'd be no way to tell the difference whether if you were writing the program, you'd have no signal to tell you I'm the parent process versus I'm the child process. So the way around this is the fork function, fork syscall returns 2 different values depending on whether you're the parent or the child. So if you're the parent, the process ID of the child is returned. If you're the child, the 0 is returned, and then of course -1 if fork fails. So that's the main trick. So let me get into actually coding this. All right, so let's give ourselves a little template here. All right, so these, as before, these, I'll give you all the header files and that you need for all of these system calls, so you can just look in my example code. So the trick is we want to save the PID, and there's like a special data type for the PID, although it ultimately is a number. And so the one thing we can do is we can use a switch statement, or you can use a conditional statement. When we fork, we can check whether the return value, so if you want to be very clever, you can call the fork inside of the switch statement or inside of the if statement, and then check all of the cases. So if it's -1, we have an error. If it's 0, then what does it tell us if fork returns 0? We're in the child, so we're in the child here. And then finally, if it's anything else, then we know we're in the parent. So even though we have a single program that we've written, now we have a way to distinguish child and parent, and we can effectively have 2 different programs running, even though it really is the same program. We now have 2 different traces of code running inside the parent and the child. Okay, so let me actually turn these into print statements so we can see what happened. Okay, so let's all right, so let's actually run this program. So I'm going to run this program here. I've forked, and you can see that even though there's a switch statement here, there's no way 2 branches of a switch statement could run, at least if you have break statements. And so you can see that both these lines, inside the parent and inside the child, are being run.
That's supposed to happen.
Yeah, so fork, we've now created two processes. Let me add a little extra code here so I'm gonna sleep both of these processes, and then let me print out the child ID as well. Okay, so I've paused this program, and you can see that there are actually two processes. So fork is the name of my program, and there are actually two processes here that are running. So without this fork command, if I had just done sleep to not quit, so let me just comment out the fork. And so now this program is still running. Here I have one process from this running, one process from this program. Sorry, this program started running. I have one process. Yeah.
What is the number of sleeping again? Number of seconds?
Yeah, it's seconds. It's seconds. So you can always look at the. That's the command. Yeah, it's number of seconds. So I would. This is just to illustrate that there are actually two processes running. So here now, when I run fork, so I've now have my fork command, and the child is sleeping for 10 seconds. The parent's sleeping for 10 seconds. So I'm going to run fork. Both the parent and child have their printf statements. So literally, when I ran fork, the entire running process was duplicated. All of its code, all of its files, and so there are two running programs. And without doing anything else, they'll both continue to run until the end. So both are, but because I did this case statement, there's different lines of code that are being executed by the parent and the child. And so we can see that, I have some existing processes running. Let me run these again. So we can see, using the PS command to show us the running processes, that indeed I have actually created a new process. So there are actually two running processes. Now these two processes are technically the same program, right? Because I only wrote a single program. I called fork in it to create a new process, but both of them are the fork command. They're both technically the same program. Those two programs do different things depending on whether they're child or parent. But it's the same program being run. So questions on this? Yeah. Oh, make fork? That's just when I run fork? Here? Or here? In the terminal, I'm just running this program on the left. So this is a C program on the left that I called fork. Maybe that's not a great name. Maybe that's not a great name for it, but I have a program called fork.c. And I have I'm using a makefile to build it, but I'm just compiling the program called fork. I could call it anything I want, fork example. And I'm just running it. So you can see there's two copies of this program running, two processes of it running. Other questions on it? Yeah. Yeah, that's a good question. I don't think it has to be. It's probably just because I don't know, I would just to throw a wild guess, I'm guessing that that process is already running. There's probably a little lag in creating the new process, so the scheduler just so happens to continue running the parent. Or maybe there's even a scheduling decision. I don't actually know, but I don't think it's necessarily guaranteed by the system. Yeah.
At what point in the code are you actually determining the value for the parent and child? I'm sorry.
Oh, so the switch statement is doing it.
Okay.
So we could also have written this to make this, maybe I should make this a little less C-like here. So we could have written it like this, where I just say, if 0 equals PID, then I'm inside the child. Maybe this is a little less esoteric. And I could have written it like this. Or, I could say something like, if PID is greater than 0, then inside the parent. Could also have written it like this. So the book, the Linux Programming Interface, uses this kind of clever switch statement. Switch statements can be more efficient. Can be more efficient.
I was just saying because of the, I guess PID is where you're getting strict.
Yeah, that's right. It's the test of PID.
And fork is passing that over.
Fork is giving you the PID, and depending on whether you're in the parent process or the child process, that number is going to be different.
Okay.
That return value is going to be different. So this, even though it's the same running program, there's a program value that differs between the, and so you can give the impression that there's two different running programs, but really it's just a different path through the program.
So they both, because it's being forked, they would be both running at the same time?
Yeah?
Where does fork pick up off of?
Where does what?
In the child program, where does it pick up off of? The beginning of the program? Does it start again?
They're literally duplicating all the state, including the position in the program that you're running. So as soon as fork is called, go ahead.
Oh, so that's why child also receives the return from fork.
Exactly, yeah. So the program counter is also copied. The program counter is the position in the program that's being run in the processor. And so as soon as you run fork, as soon as the return, I don't know exactly when it happens, before the return or after the return, but a new process is created, and the same program counter, the same position, probably the position right after fork, is for both processes. And so like here, or this test, so both the processes are going to run this test here, but because PID is different, only the parent process is going to say true on this. Only the child process is going to say true on this
So it allows
condition.
you to run different portions of the program in parallel?
Yeah, exactly, yeah.
Parent process runs first, right?
Well, it looks like that's what's happening. So somebody else asked this, that it seems like the parent-child is running first. I don't think there's any guarantee of that. I think that just naturally falls out of the implementation of like the scheduler, because I think I don't know, that's my suspicion. But I don't actually know. I don't think it's guaranteed to run first.
So these programs communicate to each other in some way?
Oh, that's a very good question. We'll look at that next time, process communication. There are several methods for process communication, like mapped memory, pipes. You can use the file system to do it as well. Sockets. So actually, one way to think of internet sockets, when you have two, when you're going into your browser and asking a website for their browser, you can actually just think of it as two running processes that don't know or care where they're running, but they've opened up some I/O between them. And so the API for having network communication is very, very similar to like file I/O. And in fact, there were competing standards for doing network communication. The Unix people wanted file style sockets. They actually still have sockets on Unix.
Like server socket on Java?
Yeah, same idea. These are really just files that you open that you can read and write bytes from between two different processes. It's a type of inter-process communication. So you're literally just communicating between two processes on different machines with TCP or IP. But yeah, it's a good question. How do you do process communication? And we'll look at a technique next time for, we'll use pipes to communicate between two different processes in order to implement pipes that we use in Bash.
Pipes like in the command line?
Yeah, exactly.
Wouldn't the process have to end in order to return?
Actually, no, they don't. Yeah, so we'll say it next time, but the way it works is that pipes are just files, and you write to one file, and you can read. So you write to the pipe, and anyone who can read the pipe will see whatever's written there. So they don't necessarily have to terminate to finish. Just like in a program, you can write to files as much as you like. You can open a file, write a few bytes, do some other computation, write more bytes.
So it's like an alternative to standard out kind of thing?
Actually, we'll use standard out to do it. We'll use standard out to do this. But yeah, we'll see that next time, how that works. But yeah, how do you communicate between processes? Yeah, there's all sorts of ways to do this. One is memory mapping. You can have shared memory between them. You can use files to do it, including pipes. You can use sockets. Those are some of the main ways. I don't know if there's other ways. There's also signals. They talk about it in the book, but I didn't cover that for this class. All right, questions on forking? Yeah.
What are some of the use cases for fork? Like you write a C program, you have like the fork command there. Wouldn't that mean that the child process is like limited to the exact same scope as the parent process?
Ah, that's a great question. So why? So if you just do fork, if you ever want to have any multiprocessing, you're going to have to write just like one giant program, and but fork, if you want to actually create a new running program, that's a different program, fork is paired with exec. So let me go back to the diagram here. So at least what we're going to use it for, and what fork is, I guess, typically, or at least conventionally used for, is that you fork a new process, and then so that you can have a different program running, you call exec on the child, and that will replace the current processes running program with a new program and start running that program. So this is the two-step process to getting a new running program on your Unix machine. You call fork first to make a new process, but that's the same program. It just duplicates that program. And then you call exec, and exec just overwrites the current processes program or text segment with a new one, and then starts running that. All right, so that's a good segue into exec. So let's look at exec first. And I have a simple version of exec here. So independently of fork, you can always call exec to replace your current running program. So let me again set this up, give myself a main method. Oops. Okay, so there's a whole bunch of different variations of exec, and I think I asked this as like a homework question. But for now, we're going to use this exec VE version. So just to show you the documentation. There's lots of different variations of it. I think the book goes into some of the detail on it. But it's not really important for our purposes. All of them will replace the current running processes program with a new program found at that path. So all of them take a path to a file, and that file contains the text of a program, or the binary of a program. And then there are other parameters to this. So this is where argv comes from. Argv is passed to the system via the exec command. And in this version of it, we also pass the environment. So if you remember environment variables where like path and stuff is stored. So when bash creates a new program, it actually passes in argv to the system, and then the system and the runtime eventually hand that down to main for your argv. So this is kind of where argv comes from. But for now, let's ignore those and just look at the program. So here we're going to take our program which we wrote. So let me put some text here so that you believe that I'm in my own exec example. And when I run this program, it's going to print out my own exec example, and then it's going to call the exec system call passing in user bin ls. So what's user bin ls? Yeah, this is the full path to the ls command. This is actually where the ls program is stored on our system. And just to kind of illustrate something else here. Oh yeah, sorry. Okay, so my program will print out the text, my own exec example, and it will call exec passing in user bin ls, which is the path to the ls program. And then afterwards, I'm going to print out the end of my exec example. Okay, so here is my Oh, I gotta save it. Here, I compiled it. Let's run exec. All right, so it didn't print out any of my printf statements because when I blew away the printf buffer. So it should if I do this. So this is getting into the weeds a little bit on how the standard I/O works. But here, just to convince you that I actually was running my own program, here's the text, my own exec example. And then when I run exec for ls runs, right? This is what the output of ls is. And I think I could even, should I try to do something like this, where I give it a command line argument? I don't know if that's going to work. No. Oh, right, it's the second one. So I think I can even pass it. Oh, that broke it. Let's not do that. All right, but anyway, you can see that the ls program is being executed now. But my second print statement here, even if I use this flush thing, you can see that the end of my exec example is not being executed. Why? Yeah. Yeah, well, okay, so that's sort of on the right track. So we're in the same process. So the process has not changed. So if I put a sleep here, so let me use find here as an example, because find takes a really long time to run. So let me pause it real quick. So this is my process ID here, 136449. Oh, let me do this in some long-running directory. So here's my process ID, 136479. And here's a really long-running command, find. It's the same process ID. Actually, I changed the name of it. It's the same process ID. So I haven't changed any process here. This is all the same process. All exec does is mess with the memory of the process, and specifically the text segment, where the set of binary instructions, your machine code, lives. So all exec does is it takes the same process and it just replaces the program text, the program binary, in the process, and then just starts running the code.
So it acts the program is running to its own structure when it runs it?
Yeah. Yeah, so let's see if they...
It doesn't just open it up as a separate file? Right?
No, it doesn't. No, it opens the file and then copies that binary code into the text segment of your running process. Is it weird?
Yeah.
So by itself, it's like, there could be reasons why you'd want to do this. You may have a helper program that manages running other programs, and you don't actually want to come back to your program. So, so the consequence of this is that exec never returns. Exec never returns.
But if you,
Unless there's an error, yeah.
But if you fork it and then you run an exec there, you get a different process.
Exactly, so very insightful. So if you use fork and exec together, you get both a new process and a new running program. So fork and exec together give you a new running program. And so they're decoupled, the same way that a lot of this kind of low-level programming is. It gives you a lot of flexibility. So there may be cases where you want to fork. For instance, if you have a web server, you actually may not want another running program. You want to have one program and do some multi-processing. Yeah?
So the exec on its own will just create a new process?
No, exec creates no new process. It's the same process. So just like here with this, when I exec find, the process ID is exactly the same as it was when I first ran the program. So just to show you this again. So this is the exec program 137570. So this is inside the sleep. And when I continue running this, it execs find. and it's the same process ID.
So just like, almost like, kind of popping around, like now.
So if the process contains, in memory, it contains the binary of your program. So the way, what a running program is when the system runs a program, when it loads the program, it copies the binary code into memory and then tells the CPU, okay, start at the beginning of this program and start running. And so what exec does is it takes the process, which is independent of the running program, it's this abstraction in the kernel, and it replaces that section in memory with a different set of binary instructions read from that file. That's why so fork creates the process, exec changes the running program. So if a process is a running program, then the program part is that sequence of binary code that you have stored on disk and that you compile. And the process just has a place in memory where it stores that binary code. So I think let me show another diagram. Okay, so this is from the Linux programming interface. This is chapter 6. I don't think I had you read this, but probably in computer organization, did you learn about the stack and the heap and memory layout? So in memory, there's the stack and the heap, and there's also the text segment. So that's where the program is stored. Historically it's called the text segment, even though it's machine code. It's not like ASCII text. And so when you call exec, one of the things it does is it replaces the binary code in this segment, and then starts running from the beginning of that text segment. So exec doesn't create a process, fork does, but fork doesn't change what program you're running. It just duplicates exactly the same program. And so to have a new running program, you call fork to make a new process, and then exec to change what program is running. Yeah?
So is that why that last print statement in your program is not running because exec overrides?
Exactly. That's why it's not running, because, yes, exactly right. That's why the last print statement doesn't run. Because, so if you look at the man page for exec, so exec only returns if there was an error. So it's a syscall, so you have to check, you got to check whether it had an error. If there was no error, then this function never returns. So whatever code you have after that is all dead code. Exec is not supposed to return.
So it's just aborting your program. And that's why it wasn't
Well, it's like you've called a function, and that function's running, but that function's never going to return to you.
Yeah.
Yeah. Yeah.
Would you just need to have the actual program you're executing have something inside of it to let you know that it's finished?
So even if you have that, this program is never going to be returned to because you've swapped out the program text. So this printf statement is after I call exec, this process doesn't even have the binary instructions to run printf. It's gone effectively. So exec is like one way. Once you replace your process with a running program, that program is obliterated. Your previous program is gone. It's never going to be returned to. So now you could have multiple processes. So this is where process communication comes in. If you do want to have two processes running, but you want to have them coordinate in some way, you want to signal one process, hey, I'm done with this task, let me run. There are other techniques for doing that. There's inter-process communication for doing that. But this is just for creating a new running program. That's what exec is for. All right, questions on this? All right, and I think I actually finished it in time. I think this is all that I wanted to cover. So, all right, thanks everyone. See you next week.